real nice. Got the Pythagorean triangles about to flex. Quantum theories on deck, breaking all the specs. Relativity theories, worlds getting small. Grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep. Grazing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold. Brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down. Actual education making scholars all around. Perpendicular minds, angles sharp as ice. Maths and physics, yeah, the future's real nice.
Alright, what's up everybody?
Good job.
Sorry, Windows wanted to update, so I'm a little bit late today. But... Ooh, we got Anch and Isaiah. What's up, Isaiah?
Hi, how's it going? I wanted to go over question 13 and 14 for homework 8.
Let's do it. Alright, here we go. Kudu, homework. Homework 8. Question... Which one?
13 and 14.
Let's do it. Right,
Thank you so much.
You're good, man. 11, 12. Ah, yeah, this one is tricky. I remember this one. Cool. Okay, yeah. What is the equivalent capacitance of between points A and B below? So this is one of these cases where they give you a circuit that looks kind of weird, but if you start, I guess, outlining like where the positive and where the negative ends of all the capacitors are, you can start to draw it as something that looks like that's, like parallel in series. Right now, this is really difficult. I see that, I would like to say these three things are in series, but then this is kind of screwing that up because it's in the middle of it, and this one is as well. So you can't just say these are in series and then this is in parallel with that, because you also have this being connected. So what I like to do when I have these is kind of like draw like paths. If that makes sense. So, and we're gonna call like different areas of the capacitor. So for instance, this is positive end of a capacitor. This is another positive end of the capacitor. And then this, let's go from B, I guess, right? This is going to be the negative end of a capacitor. And then this is another negative end of a capacitor. I'll put all the colors. Okie dokes. Alright. And then we have like something weird happening in the middle. Okay. Here's what I'm gonna do. I'm gonna kind of like stretch this out. So I'm gonna say this is point A. Because it definitely looks like these two things are in parallel, right? What's up, Famish?
Yeah, so I just did like the shortest path. That's how I got the answer, but I felt like it wasn't a good way.
Yeah, you shouldn't just do the shortest path is. I think I know the trick why the shortest path works in this case. I'll show you. It has to do with the potential. Because these are all the same capacitance, that's why it works. So, okay. So you definitely have this red one here. And then we also have... Yeah, you don't want to do just the shortest path because... because having other capacitors that aren't along the path still affect the capacitance. Okay, so then I see, and then I'm going to start at the other end here for B. Or, yeah, whatever. And I'm gonna make it do a blue end here. Dun, dun. Oh wait, my chat's not working. One second, let me chat working. Chat. There you go. That's all working. Okay. All right, and then we got the green one here. Okay, so then let's see like kind of what's happening in between. So it looks like I have what would seem to be like the positive end of this one. But then it's also connecting to here. Okay. So I have this connecting over here. Uh-huh. Okay, and then I have Famished, get me some coffee too, please. Okay. 600 amps would not be a good idea for this, guys. Okay, there we go. So we got this and this. Aha. Okay, I think I remember why this one is the way it is. Okay. And then you have this like capacitor just chilling in the middle of them. Okay. You see how this is just chilling right here? This purple one. Okay. So, because these all have the same capacitance, and they're like symmetric, what we can say is that the voltage along this this like branch will equal the same voltage across this branch. So the delta V here is equal to 0. So for instance, let's say you had like I don't know, like plus 5 volts here, and let's say you had minus 5 volts here, right? That means you have a potential difference of 10 volts across this branch, and you also have a potential difference of 10 volts across this branch. And remember that like things in parallel, so everything here has the same, the entire line here has the same voltage as the line here. So if the voltages on the two branches are the same, then technically the change in voltage across this middle capacitor is 0. So this doesn't even contribute to the capacitance, is what we say. As long as these are all like the same capacitance. If this was, for instance, like 2C, the issue is that, so voltage along the whole line is equal, but within the line, the voltage on this would not be the same as the voltage on this. And so wherever this is measuring something would be different than where it's measuring voltage over here. So, yeah, in the case of all these capacitors are the same, you can ignore this middle one. And now this is just a simple case of you have 2 capacitors in series which are in parallel with another 2 capacitors in series. Yeah, this is kind of a tricky one. I remember this now. And then do you remember how to find the capacitance of this and this, like, in series? Well, each one of these, right? So this would be C total would be equal to 1 over C plus 1 over C, all to the minus 1. So that ends up being 2 over C to the minus 1, which is then equal to C over 2. And then these two are in series, and so they have the same thing, C over 2. And then now you have two big capacitors in parallel, and capacitors in parallel add up nicely. So now it's just this. So now this is C over 2. This is C over 2. And so then these two together in parallel, C total is just equal to C over 2 plus C over 2. So you should just get C. I think the answer is just C for that one. And yeah, it is. It is just C. Bum, 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 bum. Yeah. Does that make sense, Isaiah? How we did this one?
Yeah, most of it makes sense. Could you just explain like the voltage being 0 there, and then I forgot like how does voltage get maintained in series and parallel?
Yeah. So whenever you have branches that are in parallel, the total voltage of this branch is equal to the total voltage of this branch. So whatever. So if this is V, then this entire branch is also going to be at V. And then this entire branch is also going to be at V. I realize the yellow, wow, it's impossible to see. Let me say that. There you go. So this total is equal to V, and this total is equal to V. Now, the things in series, so within that branch, they don't have the same voltage, but their voltages add up to the same voltage that the other branch adds up to. And then and that's also the voltage that's going like into the parallel branches. So in this case, because the total voltage of this branch is equal to the total voltage of this branch, and because within the branch you have the same capacitances to the left and the right, that means whatever the voltage is here will equal the same voltage here. If you did this, for instance, let's say you connected them this, let's say for whatever reason, I don't know. Let's say that like this, it was connected this way. This would not work. Because now this is at a different voltage than this thing is. In this case, I feel like this would be at like -5, and then this would be at like +5. So now they're not at the same potential. But in this case, by symmetry, because that capacitor in the middle is connecting two branches that are identical, then the voltage it measures here and the voltage it measures here are the same. And so the voltage on the capacitor, which is really the difference in the voltage between the plates, that's equal to 0, which means this doesn't even behave as a capacitor. It's just kind of like a dummy thing.
Okay, I see. Thank you so much.
And you want me to do 14 too? Or next? Yeah? Okay, cool. Let me read my chat real quick. Evan Macmillan 6743 says, "Hi, I'm taking circuits next semester. Do you have any advice on how to study and understand it well?" Yeah, it's interesting. I was saying this to my class today. Circuits can get kind of tricky because they can like present things that look like this, and you have to. Some people just have a knack for the spatial reasoning to be able to like, I say like pull things apart and like stretch them in certain ways to make it look like something that's easier to like comprehend. Like as it stands, this is very difficult to comprehend as a circuit. But once you pull it out and say, oh, well, this is also the same equivalent circuit. Equivalent meaning that the points connect to the same places. This is very easy to see that it's just, oh, it's two parallel circuits and then there's a series circuit within each one. So I would say if you want to get good at circuits, you want to first identify if you have like a knack for being able to pick out like series and parallel things. And if you don't, doing a lot of practice so that you can kind of build that recognition. Like a 9-volt battery and ponder. No, stop. So yeah, if it's a basic circuits class, I imagine you'll just be doing like series and parallel things. You won't be doing anything crazy. So I would maybe go through some practice questions to try to like get good at identifying series and parallel things. And then beyond that, if you take more advanced circuit classes, you get into what's called like mesh analysis and node analysis. Those things basically use what's called like Kirchhoff's loop laws and Kirchhoff's junction laws, or so it's called like KCL and KVL, Kirchhoff voltage loop, Kirchhoff voltage law, KVL, and Kirchhoff current law, KCL, which we will learn in class. I think tomorrow we're gonna do the Kirchhoff laws. But those are like kind of like, I say, like engineering hacks to be able to figure out the voltage and current on things by using some fun little tricks. So yeah, AC circuits is you have to take AC circuits. Yeah, we don't do AC circuits in this class, but AC circuits requires they're called phasors, which requires a lot of like complex analysis. Yeah, for sure. A lot of imaginary stuff. Okay. Yes. Yeah. Oh. So you are going to do Kirchhoff. You're going to do mesh analysis. Yeah. The other thing is it's called like Thevenin analysis. Thevenin voltage. One second. I'm just going to go a little bit off topic to show people. So, yeah. This like Thevenin. I think it's Thevenin. I can't fucking pronounce it, but this is also very useful things. These are tricks that you use to be able to figure out the voltage and the current across kind of more complex systems, especially when you start having voltage sources and current sources which are independent. Again, for my UCLA class, we don't cover any of this. This is probably like an electrical engineering circuit class that you would take. Or if they do upper division circuits in physics, you would definitely do stuff with this. But we don't need it for this class. Yeah, Thevenin. Or you took it in mechatronics. Cool. Yeah. So that's another thing. There's just a lot of cool tricks. All right, let me see. The equivalent capacitance between points A and B is C1. What is C2 in terms of C1? Okay, so all of these things are C1, but these things are C2 is what they're saying. And they're saying the equivalent capacitance is also C1. This is fascinating. Okay. Maybe there's a trick, maybe there's not. So, first thing I see, like big picture. So, big picture, if I were to like talk about things, I see this and this being in parallel. I'm like, okay, cool. So, that's like the last step I'm going to do is put that top branch and that bottom branch in parallel. Okay, but looking at this, there's something complicated here. I'm like, well, I see this and this and this in series. Okay, so that's another rabbit hole we got to go down. But then even within that, I see that this and this are in parallel. And I think that's the last thing that, or in this case, the first thing I have to put together. Okay, so let's do the capacitance of these two together. And sorry, is this a C1? Dude, this image is garbage, dude. What? There's a trick here. If you say open image and then you put a number at the end here. Wow, that is so much easier to read now. I told them to fix this. I said, come on, devs. What are you guys doing? Why are all your images hella blurry? Wow, yeah, there we go. Look how nice that is. But yeah. Okay, there we go. Okay, cool. All right, so let's do these two in parallel first, okay? So capacitors in parallel just add up. They're the opposite of like resistors in parallel. So I would call this like together like C12. And I would say that C12 is just equal to C1 plus C2, okay? All right, now I have this and this and this all in series. So I don't know. Let's figure out what like this thing would be. We'll call it like C1112, right? Because it's C1. Or here, let's say C1121. It's C1, C12, and C1. And that's a little bit trickier, right? Because that's 1 over C1 plus 1 over C1. Sorry, 1 over C1 plus 1 over C12 plus 1 over C1. All to the minus 1. Okay. And then we have that in parallel with this. So then, yeah. this is in parallel with this. And so that would be C1121, 2. So this is C1121, this is C2, and those adding together would just be C1121 plus C2. Okay. And then this whole thing has to equal C1, is what they're saying. Okay. So, what is C1121? Well, it's this. So I'm gonna like plug this in. So I'm gonna say, cool. So that plus C2 is equal to C1. Yeah, Evan, the reason is we stream on 3 different platforms. So, the Twitch chat stuff will show up on the side, but it doesn't show up within YouTube. Oh, interesting. Okay, whatever. Yeah, you guys figured it out. All right, and then C12 is C1 plus C2. Okay, so now we have this. This is kind of cool. Eep. Oh, you have? Okay, my bad. Yeah, okay. All right, so then this is C1 plus C2. Okay, and then we say, again, plus all this. And wait, what are they having us solve for again, dude? What is C2? Okay. So I need to solve for C2, but C2 is here and C2 is also here. Okay, well, C1 and C1 is 2C1. Alright, so we have 2 over C1 plus... Oh, okay. Okay, plus C2 is equal to C1. Oh, sorry, this is to the minus 1. Okay, I think I need to combine these denominators. It's going to be annoying, but whatever. So, I think you multiply this one by C1 plus C2. Right, over C1 plus C2. And then we're going to multiply this one by C1. All over C1. So then I get 2C1 plus 2C2 plus C1 all over C1 times C1 plus C2. But then this is all to the minus 1. And let me move that over. I'm going to say that's equal to C1 minus C2. Okay, but then this is an inverse, so I can flip this. So then I get C1 times C1 plus C2 over, that's going to be 3C1 plus 2C2 is equal to C1 minus C2. Man, this is just an absolute terrible mess. Let me see what the answer is. Okay, the answer does suck. Okay, that makes sense. All right, okay. I think I see what we're going to have to do then. I think this is going to become a quadratic. Yeah. Because, wait, what are we solving for? We're solving for C2. And C2 shows up a lot of different places. Okay, let's just do it. Okay, C1 squared plus C1 C2 is equal to this times this. So now we got to FOIL things. So this is 3C1 squared minus 3C1 C2 and then plus 2C1 C2 and then minus 2C2 squared. Okay. Let's try to cancel some stuff. So this cancels with one of those. I get minus 3C1 C2 plus 2C1 C2. So this will cancel out with all but one of these. And then I'll minus this one as well. So then this will become minus 2. So I have 0 is equal to 2C1 squared minus 2c1 c2 minus 2c2 squared. Okay, put it all to the right side because we're solving for c2. So I'm going to say 2c2 squared plus 2c1 c2 minus 2c1 squared is all equal to 0. This is now a quadratic in terms of c2. So let's say like c2 is equal to x. Then I would have like 2x squared plus 2c1x minus 2c1 squared is equal to 0. And now you can do the quadratic formula. So x, right, is equal to negative b plus or minus the square root of b squared minus 4ac. Oh, actually, wait, do they all have 2's? They all have 2's. Oh, that's so nice, actually. Yeah, fuck that. No, here, let's get rid of the 2's. I didn't even notice that. Okay, goodbye. x2 squared plus 2c1 minus c1 squared is equal to 0. Uh-huh. Okay, what multiplies to negative 1 but adds up to 2? Oh, that doesn't work. I might have a minus sign wrong somewhere. One sec. Because I get the... Okay, because if I do the quadratic formula, I'm going to get negative 2 plus or minus square root of... Or it's going to be negative 2c1 plus or minus the square root of b squared. So that's going to be 4c1 squared. And then it'll be plus 4c1 squared. Oh, maybe not. X equals negative b plus or minus the square root of b squared. So it's going to be 4c1 squared minus 4ac. Okay. And then all over 2. And then this is now equal to c2. What's up? Aunt, you're raising your hand. What's up? Do you want to say something?
Oh,
you can say. You can interject at any time, by the way. You can just tell me like what's going on.
Oh, okay. I just noticed you carried over the 2 and it cancels out.
Yes. Where? Which one?
In the middle, like for the 2c1x, like shouldn't the 2 cancel out? So it'll be x squared plus
Yes.
c1 minus.
You're so right.
c1x.
Thank you. Yes. Good. Yeah, you can always just unmute yourself and just yell at me. I appreciate you doing the raise your... I was like, raising the hand? Who's raising their hand? No, you're good. All right, let me see. So that's negative c1 plus or minus the square root of b squared. So that's going to be 1. Oh, okay. Okay, so then we get negative c1 plus or minus c1 times the square root of 5 all over 2. Okay. So I think, and I think you need the positive one, right? It wouldn't make any sense to have the negative one. So I think you want C1 or C2 is now equal to C1, and that's going to be negative 1 plus the square root of 5 all over 2. Is that the correct answer? Yeah, negative 1 plus square root of 5 all over 2. Wow. Okay. That's a huge pain in the ass. I'm not gonna make you do that on a test.
Zoom out real quick.
Yeah, of course. Yeah. Here, let me just download this as an image, and I'll just dump it on Canvas Fire for you guys. What this was question 14, homework 8.
Yeah, I struggled with this one because I was like, where is this going?
Dude, it's a pain. It's an absolute pain. Wait.
Do you think we'll see something like this on Friday?
No,
Okay,
absolutely not.
like the ones that really took me a long time on this homework were the ones where you just had to like calculate the circuit's capacitance from like this weird shape.
I mean, yeah, those you'll definitely have to do. There's definitely a calculate the capacitance from a weird shape question. All right, this was homework 8, question 14. I'll just say went over during office hours. Okay, cool. Homework 8. Okay, cool. Do we have up to... Oh, we do have up to homework 10. Okay, great. Okay, cool. So, yeah, there's the image. It should load for you if it's high enough. resolution. But yeah. Any questions about this one? It's okay if you want me to like re-go through something. It's cool.
No, but can you go through number 12 and 13?
Yes, number 13, I just did here. I'll show. So this one is kind of weird, right, with how things look. So from the original thing, one second, let me pull up the image of the original one. This one, right?
Yeah, I was able to get this one after I guessed for the second time, but in my
You don't need to
answer
guess.
work that I got, my final solution was the like the whole equivalence for the circuit is just
Yeah.
equal to just 1 coulomb, which
Or
I
1
don't
C.
know.
So
One-
C is capacitance, yeah. You're
one
good.
capacitance, sorry.
You're
And
good.
it's just whenever I was doing this, I had to disclude the capacitance of capacitor 5 to get that answer, and I don't think
Yeah,
that doesn't
the
make sense.
the middle one, the getting rid of this one, the middle one, is this
Uh,
capacitor 5?
No, capacitor 5 is the one closest to B.
Yeah, you don't want to get rid of that one. Yeah, so let me explain why. So this is what the original circuit is that's given to you. And this is kind of a mess because you see like, oh wait, these are in series, but then like this is in parallel with some of them and this is in parallel with some of them. It doesn't really make sense that way. So what I like to do is I like to draw out like what the paths are. So for instance, going to this capacitor, I drew out like a red here and then like a pink here. And I'm like, oh wait, so these two ends are in parallel with each other. And so that's what I draw. I'm like, so going to this capacitor and going to this capacitor, these are in parallel. And then I work from the other side and I say, okay, let's come from the right side here, from B. Where do those sides connect? It's like, oh, well, that connects to whatever, the right end of this capacitor and also the right of this end of this capacitor. So that's these two capacitors in parallel, or at least those ends. And then I say, oh, okay, well, this capacitor does connect to this one by like a direct line, which is the teal I showed here. And then this capacitor connects to the end of this capacitor by this like gold line. So then what's left is this purple capacitor that's chilling, that's basically bridging the gold line and the blue line together. And so here's the argument, is that if this circuit is symmetric, do you see how you have C and C, C and C? Then the voltage that gets measured here will be the same as the voltage that gets measured here. So the change in voltage there is equal to 0. And so it doesn't count as a capacitor. And the reason for that, as I was saying, is that anything, so the total voltage along a line that's in parallel with another line, these both have the same voltages, the entire line. Now, different points, that's not to say the voltage is the same everywhere along the line. That's not true. So, for instance, in the case of capacitors, this ends up being like +5, and then this is, I think, like -5, and then this is +5, and then this is -5. But because these have the same capacitance, right, it means that they'll have the same voltage on each of them. If these didn't have the same capacitance, then they wouldn't necessarily have the same voltage. Because things in series have the same charge. And remember that, like, Q equals VC, or we could say that V is equal to Q over C. So, if things have the same charge, then whatever has more capacitance ends up having less of the voltage along that line. So in this case, you can say like, oh, hey, there's 5 volts along this whole line. There's 5 volts along this whole line. And because these things have the same capacitance, and then they also have the same charge on them, because this and this has the same charge as this and this, that means that the voltage we measure here will also be the same as the voltage we measure here on the teal. And so there's no difference in voltage between that middle capacitor, so there can't be any charge on that capacitor. So it doesn't contribute to the capacitance at all.
Okay. Yeah, I didn't draw out that whole diagram, which I think probably would have helped.
Yeah, no, and this is a trick. Again, when I saw this for the first time, I was like, I had no clue what the hell this thing was. And then my general trick is to, I'm kind of at an advantage here because I have colors and shit, but like to draw out what the branches are and then try to like stretch it out into things that look like nice series and parallel circuits.
Okay.
Yeah. And then what was the other one? You wanted help with, so I did 13, I did 14, 12?
Yeah, 12 is just the easier version of 13.
Oh, okay. Yeah, 12 is the same thing then, I guess, right?
Kind of, yeah.
Well, actually, let's just do it. Screw it. Let me show my thing. Mia! Yes, what's up, Mia? Yeah, welcome to office hours. Welcome to office hours. I'm doing mainly physics stuff right now for my UCLA class. But if you hang around and have other questions, you can always submit them to our website, and I'll do them afterwards. The students have an exam coming up, so I want to help them out. All right, let's see. Okay, this one. Again, I kind of do the same thing here. I'm going to draw like a red one to there. And then like... Ooh, man. Oh, this is actually really weird. Ooh, what's going on here? Okay. All right, let's just draw these two to start with. I think this will make things better. Okay. Oh, man. Okay. Yeah, so this is C1. And then I say the end of whatever. This is also in parallel with the end of C3? Okay, let me see. Because this is probably the minus end. This is the plus end. It actually doesn't matter which one you call plus or minus, as long as it's consistent. Okay. Alright, so let's do that. And then I'm saying that this also connects to the end of that. Okay, I think. Oh, okay. I think I'm gonna do this. I'm gonna do this. Okay. Yes, okay, cool. All right, so that goes, so, actually, I should have drawn this in a different color. Let's do this. Let's make things thicker. Okay, so that connects to that one. And then also it connects to the end of, one of the ends of C2 as well. So we're going to say, like, from that gold, you also have this, where this is C2. Okay. And then I'm saying the green here also connects, let's do this, also connects to the other end of C1. So it's going to do like that. And then it also connects to the other end of C2. So then I could say, like, it does this as well. Okay. Okay, very cool. I see. So this is just three capacitors in parallel. Do you see how, like, so here's kind of the rule with circuits. You can move things wherever you want as long as they don't cross, like, junctures. So as long as this, like, doesn't, like, cross up here or something. So this can come all the way to here. And now you for sure have three capacitors. Yeah. You see it?
Yeah.
If you think about it in your brain, you're like warping this thing and then like you're pulling it apart. Then it looks very easily like, okay, cool. This is just what is it? 1 over C1. No, so parallels, yeah, C total. So it's equal to C1 plus C2 plus C3. Because these are in parallel. Okay, cool. Yeah, that one's fun. Yeah, so just get good at just drawing paths and then trying to move things around to make them look like they're just basic series of parallel circuits.
All right, can you do number 7 then?
Yeah. Okay, this is homework 8, question 12. I'll post this on Campus Wire as well. Dump in there, come on. This is homework 8. Okay, number 7 is what you said?
Yep.
Okay, cool. Uh-huh. Oh, energy. Okay, cool. Is this what you want? Yeah, the energy one?
No, wait, hold on. For homework 8, actually, it was the question where it's the repeating circuit.
Oh, question 9?
Yeah.
Oh, this is an infinite series? Oh, this is fun. Okay, find the capacitance of an infinite circuit formed by the repetition of the same link of two identical capacitors as shown. Oh, wow. The fuck? Okay. What? I'm guessing this is gonna be like some sort of like geometric series or something. Whenever they say like repeating things, it's an infinite series that they hope like goes to some it converges to some value. I'm trying to think how this is working though. Because okay, for my ends and they find the capacitance of an infinite circuit. I assume they're talking about this is connected. All right, let's look at it this way. Wow, thank you, Anthony. 1,000 joules. What do I do with 1,000? I don't even know what joules are. Is that a? It's a unit of energy in physics, but I didn't know that was a YouTube thing. That's cool. Okay. And I assume this is the minus end. So then, right. Okay, I think I see. I think I see what happens. So you end up having two capacitors in series, but then, oh man, but then this. Okay, this is very cool actually. It's the thing teens use to feed their addiction, Juuls. Oh yeah, those no. Juuls got banned, bro. Or all the flavored pods got banned. Okay, I think I see what's happening. Okay. Oh, this is really cool, actually. Okay, so you have... This is capacitor 1, which is then in series with this whole thing. Do you see how, like, this is in series with this?
It's in series with the blue one and...
Yes. And the two pink.
The two pink, but the blue and the pink are in parallel, right?
Yes. But the blue is in parallel with the two pink, and the two pink are in series. do you see how this becomes like an infinite thing? Because then this is in parallel with these two things, which are in series. Yeah.
Oh, okay.
Do you see how like this is in it's like this is in series with this, but this is in parallel with this.
Wait, how is the blue one not in parallel with the pinks? Because
it is.
You can.
Sorry. This capacitor is in parallel with these two capacitors. Oh, which is also in parallel with these two capacitors, which is also in parallel. Okay, I think I see it. So it's equal to a single capacitor here, right?
Mm-hmm.
Which is in series with another capacitor let's call this like C1. I'm gonna call this like, sorry. This is the thing about like circuits. It's the visualization stuff, which is kind of tricky. So let's call this like C1. So C1 is in series with whatever this garbage is, and that garbage is another capacitor in parallel with infinite number of other capacitors, which are two capacitors, I think. Oh man, it's a repeating series is what it's going to be eventually. Let me think. C1 is in series with C2, which is, this thing is in parallel with C, which is in series so this is in parallel with another capacitor that's in series with another capacitor that's in parallel with a capacitor in series that's, oh man, oh, also with a capacitor that's in parallel. Oh, this hurts my brain. It hurts. It hurts. This hurts. This hurts my brain so much. Okay.
Wait, was that Rick and Morty?
That was, yeah. I think I have a couple of these. Yeah, I have when Drake's like, it's like,
Chris Brown dancing.
Okay, this is gonna be 1 over C. Okay, I agree with. So anytime we do things in series, it's 1 over C plus something, right, to the -1. Yeah.
Yeah. So okay, if C1 is like the very first one,
Yes.
that's going to be in series with C2, and I guess the first pink one, C3.
Yes. So this is in series with C2. So it's in series with 1 over C2, but C2. So it's not in series with just C2. It's in series with C2, which is in parallel with let's say like C3.
Okay.
Do you see how this is in parallel with C3, but C3 is technically also in series with this. So it's like C. This is not just C3. Now this is 1 over C3 plus 1 over C, and then this is like to another like -1.
Oh, and it keeps going forever.
And it keeps going on forever. Yes, exactly.
That is very confusing.
It is. This is not on the exam, don't worry. I think this is just kind of like a fun little puzzle is what they put on here. Definition of fun is like, yeah, I know. You're like, it's not fun. I think it's really cool, actually. I wonder how they like, oh, man. Oh, man. That is so cool. Because then this thing is technically C plus. No, I think that's also like, yeah, it's C plus 1 over C plus. I actually don't know. I actually really don't know what this goes to. What's the answer? Screw this. The answer is that same square root of 5 minus 1 over 2, which that was the same one as this. That's what this one was as well. Question 14 was also the same thing.
That's weird.
How the hell? Wait, one sec. I think there's probably a solution on this one. Let's look. Solution. Okay, cool. There we go. Yeah, so we were on the right path, ladies and gentlemen. We were on the right path. Except this is looking all sorts of weird. Since C naught is the capacitance of the infinite circuit, the capacitance of the circuit with one additional loop must be equal to C naught. Okay, wait, whoa. Sorry, was that part of the question? No. Excuse me. Okay. Since C naught is the capacitance of the infinite circuit, the capacitance of the circuit with okay. This is kind of like some weird like real analysis number stuff. So they're saying like at infinity, this has some capacitance, right? But adding an additional loop shouldn't add any more, like it should add negligible additional capacitance. This is a math thing for sure. This is beyond what like we're teaching in this class, but so for instance, this whole thing has a capacity equal to C naught, which is, let's just say, n equals infinity loops. So let's say we just kept doing this for an infinite amount of them, right?
Mm-hmm.
So then the question is, if I add just one more of these things, like one more of these, that should be the same capacitance as it was when it didn't have that additional loop. Because every time I add a loop, I'm adding like smaller and smaller amounts of capacitance. So eventually at infinity, adding another loop adds an infinitesimally small amount of capacitance to it, and so you should get the same capacitance. So this is what we had. Remember we had like C total was equal to 1 over C, this is all to the minus 1, right? 1 over C plus 1 over C. And then they say, wait, plus C naught. 1 over C plus C
It
naught.
looks like there's a typo, like 1 over C naught instead of 1 over C, maybe.
Well, they carry it through though, man. Right?
What is
Oh.
C0?
No, you're right. No. Oh man. One sec. What the helly? What the helly? Where the hell did they go from this to this? I agree. Kind of. Wait, why is C not 1 over C though? Okay, wait. They flip both, and they say that 1 over C naught is no. That doesn't make any sense to me.
I think they just forgot the subscript, maybe on the
think so?
right hand side.
You think this was supposed to be C naught?
I don't know.
I don't know either. One sec. Let me think. If they did forget the subscript there, let's see if that's right. So then you get C plus C naught. Okay. Yes. Yeah. I think you're right. I think they did. I think you're right. They did forget the subscript here. Okay. Here's my question though. Why is this C naught? Okay, yeah, take a look at it for me. Let me draw. Sorry, let me get this image again. Which one was in this one? Where was it? Where's this image? I like almost see it. I'm so close. Okay. Okay, so we're saying if this whole thing here is C naught, okay? And then let's add, let's add one additional loop, right? Let's add one of these, yeah? So this is adding one additional loop. Which, if we have infinite number of loops, adding an additional loop shouldn't make that much of a difference. This is kind of some like mindfuck stuff where you have to say like, well, what is infinity? Like infinity isn't a number, it's a concept. And it's, if I have the biggest number of loops that is ever imaginable in the universe, then the addition of one more is inconsequential. It doesn't really matter. This is beyond physics. This is kind of like real analysis. Is what this really is. I think. Math people yell at me if it's not. I'm pretty sure this is like real analysis. Okay, so for here, let's imagine this is just a capacitor, right? So let's imagine that this whole thing is a single capacitor like this. N equals infinity, n approaches infinity. Yeah, I know. Technically true, yeah. Let me think. How did that work again? Sorry. Okay, no. This is C naught. So we have just this. Okay, that's what we have. There we go. This is C naught. So this whole thing, everything that's already been done, we'll say like as n approaches infinity, is equal to a single capacitor. We're going to say which is equal to C naught. And then we put one more loop on it. And I want to say, what is this total capacitance? Well, so C total here would now be equal to something in series. So it would be equal to C naught in series. So that's equal to C naught in series. No, sorry, C naught in parallel with 2 C's in series. So that would be equal to C naught plus 1 over, so 1 over C plus 1 over C, I think. That's not what they get. One sec. They say it's in parallel with, so that's, no, that's in, no, sorry, that's in series. Okay, no. They want it in series. They're saying, it's C in series with C and C naught in parallel. Huh. Okay, one sec, let me think. C in series with C and C naught in parallel. Oh, okay. Okay. I think they're saying this. Let me see if that makes sense. Right, okay. That's C in parallel with C and C naught. That's C in series with C and C naught in parallel. Does that make sense for adding another loop? Okay. Trying to think how this. Like, where do these terminals end? Okay, I have a hard time visualizing what's happening, how this is working, but I feel like you're adding another C in series with whatever your infinite capacitor thing is, and then you're also putting another C in parallel with it. Which, if I wrap my hand around it, I can kind of see that. Because this is in parallel with this thing, but then this is in parallel with this thing. But then that's in parallel with that. It's like you're adding a bunch of parallel circuits, but each parallel you add has two capacitors in series. Okay. All right, let's see. If we take this to be true. So this right here is the capacitance adding one more loop. This is the capacitance. With n approaches infinity loops. So this is like n is approaching infinity plus 1. It's basically the same thing. Alright. Then you do flip flip. Cool. And then they multiply by common denominators. So the common denominator is C plus C naught. So that's why you get this. This just gets multiplied by C. This should just be multiplied by C. And this should be multiplied by C plus C naught. In order for them all to have the same common denominators. Dude, there's a lot of issues on this question. Oh, unless this is a C naught. Ah, okay. Okay. Okay, I got it. Yeah, you're right. You're right with the typo there, Isaiah. Yeah, this has to be a C naught. Now, yeah, common denominator is C times C naught times C plus C naught. And so this only has a C on it, so it'll get a C naught times C plus C naught. This only has a C plus C naught, so it'll get a C times C naught. This has a C naught, so it'll get C times C plus C naught. Multiply it through, FOIL it, and then you solve for C naught in terms of C. And then, yes, this is the same cute -1 plus or minus the square root of 5 all over 2 times C. Okay. I'm still confused on the original setup of this. I'm having kind of a hard time. Like, this is recursion is what this is at the end of the day. And recursion is a very difficult thing to, like, wrap your head around. But don't worry. This won't get... I'm not going to put this on the exam. This is a no-no. I think if I had another, like, 20 minutes to, like, sit with it, I could probably see the recursion of how it's working. But, okay. Yeah. Don't worry about that question. But the correct answer is here. Square root of 5 minus 1 over 2. Recursion's easy once you've mastered recursion. Dude, stop, dude.
Oh, God!
Don't do that. No.
No, God, please, no! No! No!
Recursion's easy once you've mastered recursion. Oh, that's so meta. Okay. Any other questions from you guys? Sorry, I was banging my head against that one for a while.
can you do chapter 7, number
Yes.
10?
Yes, I totally can. Chapter 7. Potential, cool. Number 10. Oh, this one. Yes, we did this one. Yes, I'll do it again because I think I should get this one right this time. Yeah. Okay, it says an electric dipole is placed in a uniform electric field E, where E is parallel to P. One of the equipotential surfaces is a sphere. Find the radius of the sphere. Okay. So we need the equation for what the potential is of a dipole, which this is given somewhere in here. Here, the electric potential of a dipole. They do give... Well, there, here's what they give for it. So from here. Okay. So the electric field, the potential due to a dipole is equal to 1/4 pi epsilon naught. So this is just K. So V of the dipole is equal to K. And then we say P, so that's the dipole moment, dotted with R hat all over R squared. Okay. Now there's also an electric field, which we say is in the same direction as P. So there's also an electric field here. And so we remember from V over D is equal to E, right? This is potential over distance. Potential over distance is equal to electric field. That means that potential is equal to electric field times distance. Also, this came from this, right? V is equal to like negative E dot dr. But if the electric field is constant, say they say it's a uniform electric field, then you can just pull that out. And you just say, okay, well, V is equal to E times X. I think it's negative. I think it's negative. I want to say it's negative. Let me double check. Yes. Right, because let me think. If you have a bunch of positive charges here, a bunch of negative charges here, then potential needs to go down as you get further away from it. Yeah, so it's negative EX. Okay. Okay, so that's the potential due to the electric field. Is EX. Let's call this direction the X hat direction. Okay. Then if P is pointing this way and R, which is where you're measuring the electric field, is like R hat here, then P dot R is going to be P cosine theta. So K is going to be equal to P cosine theta. And then this is going to be over R squared. Then I think we're going to do this minus E, but then I only want the amount that's along the electric field. So wait, I wonder if I could say that that's equal to E R cosine theta. I think I kind of like that. Yeah, let me do that.
Oh,
What's up?
I was wondering, like, cosine is like adjacent over hypotenuse, so
Mm-hmm.
like maybe I'm a bit confused, but like, would it, like, why is it p cosine of theta? Because like cosine of theta would be
Because it's a dot
p.
product.
Oh, okay.
Dot products are always cosine. And again, if I want the amount of r that's in the same direction as p, and this is the angle theta, this is a good question. No, totally good question, Isaiah. Do you see how this makes a right triangle? So how much of this is in the same direction as this? It's the adjacent.
So cosine of theta would be p over r, right?
Oh, that's if you're doing. Wait, no. Bleh. Yeah, cosine of theta, yes, would be equal to p over r.
Okay, thank you.
Yeah.
Oh, so why are we using like p cosine of theta?
Because I'm doing p dot r hat. This is okay. I think I know what I want to do here. I think I want to make this like a vector. Well, no, because potentials are scalars.
Well, doesn't the electric field and the dipole like point in the same direction? That's why it's cosine, right?
Well, this one needs to point at the same direction. I agree.
Because like dipoles have to point in the same direction, but you're trying to solve for the electric potential.
Yeah, which the potential doesn't have a direction. The potential is a scalar, is the key thing.
Okay, it's a scalar.
Right, so I'm tempted because I want to write like r hat as equal to like r vector over r, but then my potential. Well, actually, let's just do it. Let me see. I forget if the equation works out this way. If r hat's equal to r vector, because is this a vector p? They just say it's equal to p, but I'm like, what is this? This is just a scalar. How can a scalar be dot product with r hat? That doesn't make any sense. Let me see another like web definition of it. What is this? Electric potential due to a dipole. Equation. I want the equation. Well, that's the potential energy. That's kind of cool. Okay. Electric potential due to a dipole is equal to K. Yeah, Kp cosine theta over r squared. Is that what I had? Yeah, I did. Yeah.
Well, wait, don't dipoles point from like negative to positive, but electric
Correct.
fields from positive to negative, so they would be parallel, right?
They are parallel. Yeah, but they said the electric field points in the same direction as the dipole moment, I think. Or they just say it's parallel to it.
Yeah, they say they're parallel. So like,
Oh, so that actually doesn't say whether it's in line or 180 degrees, does it?
I assumed. Well, I thought just because they were pointing opposite, like if they're directed opposite directions, that they're what's it called? Their electric potentials. One would be positive and one would be negative because they're going completely parallel 180 degrees.
Yeah.
Is that not how dipoles are? Because
No, dipoles point from minus to plus in terms of the charge, but what they're saying is that the dipole is in a uniform electric field. So that's not saying specifically that electric field is not being generated by the dipole.
yeah, they're just in an electric field. But
Correct.
I was thinking if there's an electric field, it has to be a positive and a negative side charge
Correct.
plates kind of situation.
Good. Yep, I agree.
So I'm thinking if it is supposed to be pointing from negative to positive, wouldn't it like flip itself around?
If it's perfect, the dipole would be in what's called like unstable equilibrium, right? Because if the dipoles point from minus to plus, right?
Yeah.
So in this case, if they're exactly parallel with it, it'll stay rigid because the negative end of the electric field will pull the positive end up, and then the positive end here will pull this one towards it.
Yeah. So I think
It's actually, this is stable equilibrium.
Wait, is it unstable equilibrium or?
I think it's stable because think about it. If this shifts any amount this way, and this shifts any amount this way, then this will want to restore it this way, and this will want to restore it this way.
Okay, so it would be in stable equilibrium.
Correct.
Is it like confirmed that it would be pointing one way or the other? Like,
when I see E is parallel to P, I assume they point in the same direction. The issue is that like P points from minus to plus within the dipole. E points from some positive thing generating the electric field to some negative thing.
Yeah,
completing the electric
because I know
field.
they're on the same axis, but that
I think they're in the same direction as well.
I thought they were in the opposite direction.
I think, yeah.
Because then I was like, you could do like your total voltage.
But here's the key thing:
equals
the potential, right, is equal to negative E. Right. What is this? Potential is equal to negative E dot dx, right?
Yeah.
And so if the electric field is constant, and we say it's pointing in this direction, and dx is also pointing in this direction, that means the potential is equal to negative Ex. And I think you need that, because my total potential, so V total, will be equal to V dipole plus V of the electric field. And I think I want to show that this, and if it's an equipotential, V total is constant, okay? But the only way to get two things adding to each other to be like constant is they need to add up to 0.
Yeah,
because
whenever I was stuck, I looked online and it was like everything has to equal 0. So that's why I assumed my initial assumption was correct, that they're pointing in opposite directions.
No, I think they have to point in the same direction in order for the potential to become negative. Because
Oh, wait, I thought potential. Is it always negative? I thought.
well, from this, right? Potential is negative E dot dx.
Oh, okay. I see what I did there.
Right.
Yeah.
And that's going from like, let's say going from 0 to x, right? I get, okay, cool. E is constant with respect to x, so I get negative Ex from 0 to x, and then that's just negative Ex. Okay, so I think, yeah, so this is Kp.r. This is r hat. So here's the key thing. Someone was asking me like, why is this not r cosine theta? The reason is because r hat is a unit vector, which means it has a length of 1. So when you do two vectors dotted with each other, so if I do a dot b, for instance, that's equal to the magnitude of a times the magnitude of b times the cosine of the angle in between them. This has some magnitude. We're saying that this isn't p hat, this is p. I think really this should be p vector is what they should. This is kind of an oopsies. I don't like that they're doing this, because they're even in hyperphysics they screw this up. Oh wait, no, here they have it. That's the electric field. Yeah, but where's the potential? Here we go. Yes, do you see here how they say V is equal to Kp cosine theta over r squared? Oh, they didn't show that that's because it's p dot r hat. Okay, never mind. All right, we're gonna get the same result here. This in reality should say p vector dot r hat, because you can't have just a scalar dotting with a vector. That doesn't work. It's got to be two vectors, and r hat is a vector which has a magnitude of 1. So that's why this is technically Kp cosine theta over r squared. And then the electric potential is going to be equal to negative Ex, which in this case I think is just going to be negative Er cosine theta. R is where we're measuring the potential. Okay. So then, this is equal to kp cosine theta over r squared minus er cosine theta is equal to a constant. This is v total, which is equal to a constant. So, dun, 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 dun. Dun, 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 dun. Let me think how I want to do this. Oh, because they're asking for like what the radius is, right? Yeah. Okay.
Wait, isn't is it the voltage that equals the negative integral of EF times dr, or is it just the electric potential?
Voltage and electric potential are the same thing.
Yeah, but isn't there like a situation where you have like a voltage that's like non-zero at a point in a capacitor versus like?
Yeah, so that's the change in potential then. Yes, technically this is the change in potential.
Okay.
Is what we're saying?
Because I have like V in all my equations, and like some of them are changing V, and I'm like, hold on, I'm getting confused.
Yeah, no, I got you. Okay. I remember I want this to be an r cubed somehow. How do I do that? Let me think. I think I want to multiply that by r squared. And then I want the angular dependence to go down. That's how I get something to be spherically symmetric. Let me see. I did this one yesterday. It was this one, right? Let me see. Yeah, see, negative EX. Okay, cool. And then they say it's equal to... Oh, over R cubed. Wait, that's a different formula than what they gave us. Wait, excuse me? Excusez-moi. Okay, I'm on the right track here. Oh, because X is R cosine theta. Ah, uh-huh. Okay, I think I get it. I see the trick. I see the trick now. Okay. All right. We're not going to convert this one to R cosine theta. We're going to leave this one as X. So the potential going from here up in the X direction, the potential difference there is equal to negative EX. That's the potential due to the background electric field. And then the potential due to the dipole is equal to Kp cosine theta over R squared. And then this is where I'm going to make kind of a cute little substitution. I'm going to say, well, X is equal to R cosine theta. So cosine theta is equal to X over R. So if I plug that in, now I get Kpx over R cubed minus EX is all equal to C. Okay. And then, do they combine these two? Okay, they just solve for R. Okay. Okay. So now you solve for R. So that means moving this over. So C plus EX is equal to KPX over R cubed. Move this over here, move this over here. Okay, so r cubed is equal to kpx over c plus ex. And then, okay, this is what I'm going to do. I'm going to divide the top and bottom by x. And so I'm going to get that r cubed is equal to kp all over c over x plus e. Okay. And so then cubing for r, I'm going to get that r is equal to kp over c over x plus e all to the 1/3. Okay. Now here's the key thing. If I want this, if I want this potential to be an equipotential, which means that everything has the same constant potential c, but I want it to be the shape of a sphere, I need the x position to go away, like the dependence on the x position to go away. Because what we're saying is that I'm going to have some sphere here such that the potential is c everywhere, but what the value of x is, right? Do you see how that, like, that value of x changes along the sphere? So I need whatever my equation is for my potential to not include any dependence on x. Because x is like the x component of r, where r is where you're measuring the potential. So they say here, in order to have a spherically symmetric potential, equipotential, it cannot depend on anything other than r. Or it just can't depend on x or anything else that isn't r. Because then it wouldn't be spherically symmetric. And so in order for that to hold, that means c must equal 0. Which means when we were calculating what our total potential was, right? And we said our total potential was equal to a constant c. That's why we say it's equal to a constant equipotential of 0. That's the only way you can get the same potential in a spherically symmetric shape. And so then r... Yeah, go on. What's up?
So why does it have to equal 0?
Because if looking here at the math, right? Do you see how r is the radius where the potential would be equal to c everywhere? But
Yes.
I need that radius to be constant depending on where I'm looking.
Okay.
And so x here refers to, right? This is like the x coordinate of where you're looking. Like where you're looking at potential. But on a sphere, right? Depending where I'm at, do you see how the x coordinate would change? If we're calling like x the up-down direction.
Sure.
Yeah, it's kind of like a chicken or the egg thing here. You're saying that like it has to be spherically symmetric, so thus this radius of where everything is the same potential has to be constant. The radius can't change in order for it to be a sphere, right? Spheres are objects such that the distance from the center of the sphere to the surface of the sphere is always a constant r, right? In this case, in order for that to hold, I need c to be equal to 0, such that this x dependence just like gets wiped out.
So wait, if x is where you're like viewing from, what is c?
C is what the sum of the two potentials are. It's what your total potential is. It's the potential of the equipotential. Where equipotential means like everything is the same potential there.
Okay, could you zoom out all the way?
Yes.
Wait, can you for the first diagram, can you like draw where the sphere would be?
Yes, so the sphere would be at the center, and then it would have a radius equal to the cube root of kp over e. So, for instance, yeah, it would be something like this, where the radius of this would be equal to kp over e. And P is the dipole moment, yeah.
Okay, so the sphere is the dipole, and the dipole.
No,
right?
the sphere is just an imaginary region where everywhere along the sphere, the potential is 0.
Okay.
So equipotential means that things have the same potential, but also if the potential is 0, and it's 0 everywhere as well, that's also an equipotential. Because 0 equals 0 equals 0 equals 0.
Okay. That's the, is that like a Gaussian surface then?
Sure. Yeah.
Alright. And...
Except you
or not,
don't
sorry,
really
like
want to deal with
Gaussian
like charging
it's like,
close stuff.
sorry, it's an equipotential line. That's coming off of the dipole. That's at, I guess, the center of our triangle.
Yeah, I think it's right here. I think it's located at the center of... it's located where P starts. Right, because P is a vector that points from the minus end to the plus end.
Oh, I thought P was a...
Well, actually, here's a good question, actually, sorry. Yeah, wait, where do they measure... Okay, maybe they measure it... R minus, R plus... No, they measure it from the minus point, yeah.
Will we see something like this on the exam? Probably.
I forget if dipoles are on it. It won't be this tricky. I don't think so. No, this is kind of... Yeah, V, Q, KQ, 1 over plus minus 1 over R minus. And then they say this. Uh-huh. Oh, in this case, R is measured from the center of the dipole. Okay. So, no, I was slightly wrong. So, sorry. The sphere is measured from here. Yeah.
So the R vector, that one's from the negative charge?
Yeah, let me see. Let me see.
So, if I understand this correctly, we have a dipole with a dipole moment or something like that. That's pointing from negative to positive.
Yes.
And that's a vector. And we also, outside of this dipole, is an electric field that's pointing in a direction. These dipole moment and the direction of the electric field lines are parallel. So that means they can either be completely 180 or 0 degrees.
We assume they're in the same direction. They're parallel and they're at 0 degrees. Yeah.
Why did we assume that's in, like, how did we prove that it was again?
Because that's the only way to get the potential due to the electric field to cancel out with the potential due to the dipole.
Okay, so they're pointing in the direction, so they cancel out.
Yeah.
In that case, then, since we know they're, I guess, pointing out in the same direction, we're trying to find the radius of, I guess, the equipotential circle sphere at like the epicenter of the dipole. So
yes.
So if an equipotential line can be expressed with like V equals KQ over R, then we can, I guess, combine the electric potential of the dipole and the electric field.
Correct. Yep, that's what we did here. Potential of the dipole, potential electric field.
You get some not calculus, but I guess like algebra stuff. And okay, I think I see it.
Yeah, so the potential due to the electric field, right, is negative EX, where X measures the same direction as the dipole. We're just going to say up, okay?
Okay. And the electric field in this instance, or I guess like the electric potential of the electric field, that's the negative component, but the electric potential of the dipole is the positive.
Correct.
Okay, got it. That's what I had next from yours.
Yeah, if this was plus, then there would be no way for this to be equal to 0, right? Unless R was at like infinity.
Okay.
Well, actually, not even. Sorry. If this is plus, then this would go out to infinity as well.
All right. I think that kind of makes sense. Yeah, I don't really remember doing this one very much, so I was very confused.
Yeah.
Okay.
Yeah, you would get negative radius actually. So, if this was a plus, and then you move this over, this would be a minus, and this would be a minus, and this would be a minus, and then so in order to get rid of the x dependence on the radius, it would then be 0 minus e, which the cube root of something negative is negative, and so then r would be negative, and you can't have that. So negative radius doesn't make any sense. Yeah.
All right, that's cool.
Yeah, this is kind of a, I don't, it's kind of like you're assuming what the answer is, and then you go down trying to like use math to force the right thing to pop out.
Okay.
It kind of, to me it makes sense because x is, so where you measure potential is at r, but r has x and y components, and so what you're doing is you're leaving the electric field potential in terms of the x component of the r where you're looking at things, and then you kind of leave it here as well, so that when you rearrange for saying, hey, let's assume that it's that this potential c that happens everywhere has an r that it's associated with. Well, in order for that r to be constant, like with a sphere, the radius is constant for a sphere. Anywhere you look along a sphere, the radius is constant. That means that c, the potential that everything is at, needs to be equal to 0. And then when we do that, now I do have a radius that is only dependent on the electric field in the dipole moment. And it's not dependent on where I look. So where I'm looking for the potential is nowhere in this equation anymore.
Okay.
Does that kind of make sense? Like,
Yeah, that one was confusing.
yeah, R is where you're looking.
All right. Then can we go back to if anyone else have any questions on this one?
Are you going to post this on Campus Wire?
Yeah, I can post this one right away. I'll post this whole screenshot for you. So wait, R is where you're looking. X is the X component of where you're looking. Trust me, this one took a lot of like bending my mind around it to make it make sense.
So this probably won't be on the exam, I guess.
No,
or at least
no.
nothing this complicated.
No, nothing that's complicated. X component of where you are looking.
Should I study over dipoles, just in case?
Yeah, I would study dipoles. I'm pretty sure. If I don't put it on this, I definitely put dipoles on the final. I'm pretty sure. Put R where you're looking. Okay, let me save this for Emily and everyone else, I'm sure, that wants to know about this one.
All right, thank you.
You're very welcome. Was this is homework 7, right? Homework 7.
Yeah.
Question. Which one was it? I think 11, 12.
Number 10.
Number 10. Thank you, Em. Question 10.
For homework 8, can you help me go over question 11?
Yeah. There we go. Homework 7. There you go. Should be able to see that. Okay. Homework 8, number 11.
Yeah.
Okay.
Because whenever it says 2 metal balls, I'm imagining it's like, because I looked at my equation sheet for this one. It's supposed to be like not cylinders, but spherical capacitors, right?
Mm-hmm.
And it's like one inside the other, right?
Ooh, okay.
I think that's what it's talking about. Or it's just like 2 metal spheres or balls just
Okay.
separated by a very long distance.
Okay, so what's the definition of capacitance?
How much charge you can hold per voltage?
So I would say it's equal to Q over like delta V. Right?
Yeah.
So
But in this case, so I went with the assumption that this is a situation where you have like two conducting spheres. And I was kind of confused because technically if they both have the same radius, they shouldn't be inside each other. So they should be like a distance apart. So then I started thinking if they're a distance apart, I guess they're like point charges then.
yeah, I agree with that.
So then I started looking at that more, and I just don't know where I got 2 instead of, I guess, 4 from.
Okay. So this has, we're going to assume like a charge of plus Q. This is going to have a charge of minus Q. Because this Q here in the capacitance equation refers to the plus and minus charge on each end of the plate. And we assume that the plates are at the same charge, but opposite signs, right?
Mm-hmm.
Okay. Do I even care about A at this point? Really? It says B's much... Oh, I do care about A? Excuse me? Dude, what? Oh, I see how this works, actually. Okay, this is actually kind of fun. Okay, so I need delta V. I get it now. Okay. So we say this is equal to A, right?
Yes. They have identical radii.
Love that. Okay, we're gonna call this, I don't know, number 1 and number 2. Okay. So delta V is gonna be V1 minus V2. Okay. Which this is like the potential at 1 and the potential at 2. So, not caring about this thing, what is the potential at the center of this conducting sphere of radius A?
If it's, well, if we're assuming it's a sphere and not like a solid ball, so like
Sure.
I guess like a hollow shell,
Uh-huh.
then it would be, the electric field inside would be 0. So
What would the potential there be?
the potential would be the same as what it is on the, I guess, on the outer shell.
Okay. Yeah, and what's the potential to get to the outer shell?
The potential of the outer shell would be K, I guess, positive Q over the radius A.
Good. And then so what would the potential of this one be?
That would be the same thing, but negative.
Good. And you see I have minus negative. So the change in potential is now 2kq over A.
Oh, okay. I'm starting to see it now.
Yeah. So then C equals Q over delta V. So that's Q over 2kq over A. Cancel, cancel. Just get A over 2Q. A over 2K, which I think is what the answer was, right? Yeah. K is 1 over 4 pi epsilon naught.
Okay, could you zoom out?
Yep.
Okay. Then I guess, does anyone else have any questions?
I also was thinking at the first, I was like, wait, aren't these just point charges? Like, what's the potential between 2 point charges?
Yeah, I didn't think they were point charges until like, I kept assuming they were supposed to be like when it says middle balls, like radii, I immediately went like, oh, it's like,
Yeah. I was like, wait, what's the
And-
potential?
like there's a distance B, and I'm like, why are you talking about a distance B if you're, yeah.
Yeah, the reason for that, right, if B is much, if B is much bigger than A, you can assume that A is much smaller than B. So I'd be like, wait, isn't this just the potential between 2 point charges? Which... yeah, it's kind of weird. Because if you're trying to find the potential at the point charge, that potential is infinity. Right? So if you have a single point charge, V is equal to KQ over R, right? Where R is your distance away. So if I try to find, and when you're doing capacitance, you're trying to find the potential difference between the two plates, between the two locations. But I can't figure out what the potential is at the point charge, because then that becomes divided by 0, which is just like infinite. Yeah. This is fascinating.
Okay, then I guess my last question is for number 10, because this was like one of those that kind of just rushed through, and I was like, I think I get it, but not really.
That's a great thing to ask during office hours. Yeah, it's the I think I get it, but I don't.
I'm assuming it's two like long conductors that are like cylinders, right? Or
Was
like
this
it's
homework
two-
5, by the way? The last one we did was
This
homework 5.
is that one was with homework 8.
This is okay. So homework 8, question 11.
Oh, also, do we need to know what a coaxial like cable is? Because it was
Yes.
on like.
Yes,
Hmm,
we definitely
Okay.
know what a coaxial cable is.
okay.
We did a lot of things with coaxes, didn't I? Think I stressed it a lot. Right? I think I did. I think we did it in homework. We did it in the clickers, and I think I also did it like during like the lecture as well. Yeah. Yeah. You should know how coaxial cables work. Okay. Oh, this is homework 8. I think mainly the reason why I love coaxes so much is because I had to build so many of them during grad school. Or during undergraduate, sorry. Also during grad school, I had to build a lot of, it's called like RG58. But in undergrad, my job that I got my freshman year at a laser physics lab was just crimping cables like all day. I wasn't doing any science. I was just making cables. That's kind of what happens as an undergrad. You get they hand you like a mop. They're like, hey, sweep the floors. It's like, man, but I want to do science. And I say, well, you don't know enough science yet to do science, so sweep the floors. Okay, which number? Sorry?
Number 10.
Number 10. Okay.
Do we also need to know like what a electrolytic capacitor and like variable air capacitor are?
No, I don't know what that means. I'm gonna guess that means like, wait, was it variable air?
Yeah, a variable air capacitor and a electrolytic capacitor.
Oh, electrolytic caps are just like regular capacitors. I don't know what a variable air capacitor is. That's crazy. Is it? I guess it's a capacitor that you can vary its capacitance with the amount or type of air that's in it, maybe?
I think so.
No, it's not on the test. Okay, two infinitely long straight wires have a cross-sectional radii A. The distance between their axes is B. What is the capacity? I think this is the same question. Ish.
Yeah.
Right? I think it's the same question, maybe.
Yeah, two infinitely long straight wires. Well,
It's kind of like
I don't think it is,
kind of like the
'cause you
cubes.
have-
It's kind of like the spheres, no?
It's kind of like the spheres. I imagined the two infinitely long straight wires were like capacitors. Like
Oh, they were
cylindrical
like on top of
capacitors
each
in a
other?
way. Yeah, because I was looking at the answer choices and it's like, how did you get ln of B over A and stuff like that?
Yeah, I'll show you. Yeah. So no, they're not inside of each other. They are like located away from each other.
Okay.
This does not look very straight. What the hell did I draw here? Okay. Ooh. I want this to look nice. Now it's like an optical illusion. Which way is the pipe pointing? Okay. So again, capacitance is equal to Q over delta V, right?
Yep.
So I want to know, right? V1, V2. Okay. What is the voltage due to a cylinder? So no, right?
Voltage.
Yeah.
Due to a cylinder is like, I guess the charge per area over, I guess, times the whole length. the charge per length times the length, so that'd be charge, and then I guess
I think there's
over
an
the whole-
ln. I think there's an ln in there somewhere, right? Well, maybe
Oh,
let's do.
what was your question again?
Yeah, I think you're doing the electric field. Totally cool. Okay, let's assume.
So, what were you asking for again?
I was asking what is the voltage at the center of a cylinder?
The voltage at a center of the cylinder.
Is that given to you? I mean, we can rederive it. It's okay.
The voltage at the center of the cylinder, assuming the cylinder
Is a conductor.
is a conductor, and the conductor has like a charge, then the voltage at the center of a conductor is usually the same as it is on the surface.
Good.
So the voltage would be 0, but it's an action, not a 0. It would be constant,
Inside.
some number, but yeah.
Yes. But what's the number?
I have no idea.
It's okay. Yeah. I don't think it's given actually. Like we know the one for the sphere, which was this, right? Let's derive where it comes from. Okay. So you know what the electric field is due to a cylinder. I think that's equal to 2k lambda over r.
That sounds right.
Yeah, okay. So let's remember that potential is equal to, right? So it's like, what is it? V2 minus V1, which is like, or we're going to just say it's like VR minus V infinity, which is equal to the negative integral going from infinity to r of E dot dr. So we're coming all the way from infinity and we're coming into here and we're integrating the electric field as we do it. So that's equal to negative 2k lambda integral from infinity to r of 1 over r dr. This is a nice integral, right? This is ln. Which this is actually gonna be discontinuous. ln of r minus ln of infinity. Ooh, I don't like that.
You done messed up, Aaron!
Because ln of infinity is infinite. Excuse me. Oh, you know what this is? This has to do with like why 1 over x doesn't converge, but 1 over x squared does. Okay. You can't do this trick actually for infinite cylinders. You can do it for spheres, but not infinite spheres, right? So this trick of going from infinite... The problem here is the potential is not 0 at infinity. Because at infinity away, because technically you have infinite amount of pipe that will eventually create some sort of potential there. This comes from... How much math have you taken, by the way, Jack?
Through Calc 3.
Cool. Do you remember how, for instance, like, the sum is n equals 0 to infinity of 1 over x? Like, this does not converge. But the sum is n equals 0 to infinity of 1 over x squared does converge?
Kinda, yeah. I know 1 over infinity equals 0, but I know when you get to, like, the 1 over x squared, you have, like, a special thing.
Yeah, well, so this is the reason why, for instance, this is cool. It's a little bit of a tangent, but so, for instance, like, 1 over x would be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, right? Plus 1 over 5. This would be 1 plus 1 over 2 plus 1 over 4 plus 1 over 9 plus 1 over 16, yada, yada, yada. Okay. So do you see how you're adding smaller and smaller amounts of numbers to what your previous number was? Like, it's like a running total.
Yeah.
So in calculus, you do this in Calc 2. You show that this does not converge to a single value. But this does. And what I mean by converge is that eventually, so if I were to take the limit as I go to infinite number of terms, this actually does equal a number. This one does not. It technically keeps increasing. And it's really weird for that to happen. And they kind of show this because they do the integral test. Because if you integrate 1 over x dx, you get ln of x. And again, if you go from like 1 to infinity, the issue is that ln of infinity doesn't converge to anything. It's L of infinity is infinity. But if you do the integral of 1 over x squared dx, this ends up becoming negative 1 over x, which from 1 to infinity, negative 1 over infinity is 0. And so this does converge to a number. This one does not.
Okay.
Yeah. So I think that's the issue with the potential. I think of, I don't know, do we just like ignore this and we just say like, hey, screw this? Like, I don't want to deal with this. This L of infinity screws me.
Can we just like make the integral from a to b, or like a to b minus a?
A to b minus a. Oh, I see what you're saying. But then I need to consider the electric field generated by this, though, is the problem. Right? If I want to say the potential from here to here, the issue is that I have electric field coming off of this, and I also have like electric field coming from this.
So you just like add them together, right?
Yeah, I guess so. Actually, here's the cool thing. If I want to say what the potential at the surface of a cylinder is, I think I can technically leave the ln of infinity, because when I do it for the other one, I'm also still going to get an ln of infinity, and I think they're going to cancel out. Let me look at this actually. Sorry, let me just Google this real quick. Potential at the center of an infinite cylinder, infinite conducting cylinder. Yeah, they're saying stuff about the 1 over infinity, but commercials. Wait 1 second. Let's get, okay. Dude, this guy's bow tie is rad, dude.
About
What?
finding the potential inside and outside.
Yeah, see, watch
a
out.
linear
Yeah. If v equals 0 at infinity. Yeah.
conductor.
V's.
Now,
right.
let's assume it's an infinite
Let's see what he gets. What does he get?
constant for that very small change in the, using this equation for the electric field outside. That would be the linear charge density, so conductor. All right, if we do that, times 1 over
Show me the part we screw up.
dr. Okay,
Yeah.
what is the integral of 1 over r dr? Well, we know that that's, of course, the epsilon sub
ln.
naught. To do it here, 2 pi epsilon sub naught. Sometimes what I do is I get rid of the negative sign by flipping the limits. That's one way to get rid of the negative sign of infinity. Now here's the problem.
Yeah, here's the problem.
Natural log infinity doesn't disappear. When we integrate something that's 1 over r squared, we get r in the denominator, then we plug in infinity, goes to 0. But in this case, the natural log infinity is still infinity. So what that means, now when I apply the negative sign, this is equal to lambda divided by 2 pi. Away from that, it makes no difference. So in relation to this number, this is virtually whatever
goes
it is.
away.
So the potential difference between a point at infinity and any point close to conductor is an infinite potential difference. So we cannot use this technique to try and find the potential at some point close to conductor like we did with the sphere. If it's cylindrical, we can't use this technique.
Okay, so apparently we can't do this.
Instead is pick some arbitrary point of reference like right here and then say, let's find the potential difference.
You're right, Emily. Emily, you're right.
And we're going to find the delta V.
Okay. Okay, fine. Fine. Okay. Okay, Emily's right. So, instead of going, okay, capacitive, assuming B is greater than A. So we're gonna go from B to A. I think you still have to like consider the electric field due to the other one, but yeah, maybe you just double it. Okay, so you're gonna go on, Emily.
What I did was that, like, I just calculated the electric field from a positive cylinder, and then I just doubled it.
Then you just doubled it. Let me think. I think the doubling is going to come from Okay, okay. I get it. Yeah, the electric field due to this one, if this is positive, will point from here to here. And then from here, if this one is minus, right, it'll point in. So you're assuming that, okay, there's twice the electric field in the center. Okay. I agree. I think the issue I was having is that, like, as you get close to the edge, that's not going to be true. Because the electric field of this one will be really strong. But the electric field of this one will be kind of weak. But I guess if B is much greater than A, then it's okay to just double them. What's up, Zach?
Good job.
Okay, so let's do that. Let's go from B to A. So then that's negative 2k lambda ln of A minus ln of B. Yeah? So that's negative 2k lambda ln of A over B. And then for the electric field, we're going to double that. So this was actually like 2e. So that becomes 2 potential. So then, yeah, it should be 4k lambda ln of B over A. Is that what the answer was? Well, I have the backwards of it. 4k, so that's 1 over 4 pi. 4 times 1 over 4 pi epsilon naught. Okay, so you're going to get lambda over pi epsilon naught. Oh, yeah. Lambda over pi epsilon naught, ln of B over A. Okay. That's equal to delta V, though. And then C is equal to Q over... Sorry, there's still a lambda here, right? Interesting. So that... But, Q in this case is lambda L, right? But it's infinitely long? Oh, capacitance per unit length. They want capacitance per unit length, though. Okay. So Q is charge density times length. And then... Sorry. And then we're dividing by potential. So I'm dividing by pi epsilon naught ln of B over A. And then so capacitance per unit length is I'm dividing by L. And then you get lambda over pi epsilon naught ln of B over A. And that's the correct answer. Pi
Okay, so
epsilon
that's the
naught.
capacitance over length.
Yeah. Wait. Okay, sorry. This gets on the top. Sorry, what am I talking about? Sorry. Yes. Okay. I agree. I agree with what Emily said. That when calculating the potential from here to here, instead of using the electric field just due to one cylinder, you're going to double it because you have electric field being generated from the positive cylinder towards this, and you also have electric field being generated from the negative cylinder towards it. Yeah.
Okay, so you're assuming that the electric field is, I guess, well, you're between the two. Okay.
Yeah. Well, you're going from one to the other. This is where I wonder if I kept the infinity. No, the infinity wouldn't work, though. Yeah. No. It wouldn't work.
Okay. Could you zoom out?
Yeah.
Thank you very much.
Okay, cool. Thank you, Emily, for the assist on that one. I was losing my mind.
Will you be having another office hours tomorrow?
Yes. I'll announce it. I'll probably do it at the same time tomorrow.
All right. Got it.
I
Thank you
enjoy
very
these. I'm glad you... Yeah, you're very welcome. I'm glad you guys are asking questions. Da-da-da. Zach, today is technically pi approximation day. It's 7:22. 22 divided by 7 is the approximation of pi. What's up, Emily? What were you going to ask?
Oh, I was just asking, like, do you maybe have time for one more today?
Of course. Yeah, yeah, what's up? What do you want to do?
Could you do chapter 8, number... Wait, no, not... Wait, yeah, chapter 8.
That's the capacitor chapter.
Yeah. Wait, I'm finding the number.
You're okay. A new version of Kudu's available. Wow, crazy. Oh, look at all these new versions that keep showing up.
Chapter 8, number 13.
Yes. Here, I did this one earlier, but I'll explain it to you.
Oh, sorry, wait, I thought you did number 12 earlier.
Is this number 13?
Oh, yeah, oh no, that is number 13. Oh, I didn't see that one. Okay.
That's okay. Yeah, it's just, you want to, like, take this shape and turn it into something that's easier to see in terms of, like, series and parallel. And my, like, strat for doing that is, like, connecting similar sides of the capacitors to, like, drawing these paths so that I can see that, for instance, this is in parallel with this, right? I'm like, okay, cool, parallel, parallel. And then I go to the other side. I'm like, okay, well, this side's in parallel with this side. So that's why I drew this. And then on the other side of this capacitor, that connects to the other side of this capacitor. So I drew a wire from here to here. And then the other side of this capacitor connects to the other side of this capacitor, which is the blue to the pink one here. And then that leaves this middle capacitor chilling right here. And then the argument we say is that because all of the capacitors here are the same, that means that voltage is distributed equally amongst each capacitor. And also amongst here. And then also because these things are in parallel, the total voltage on this top leg is the same as the total voltage on this bottom leg. So that means the voltage being measured here is the same as the voltage being measured here. Which means that middle capacitor doesn't count.
Okay. So...
yeah, go on. Sorry.
Wait, so... Sorry, what did you say before that about the charge of the top and bottom ones?
Yeah. So when we look at these two capacitors, right, which are in series with each other, we know that capacitors in series have the same charge, okay? And if they also have the same capacitance, they also have the same voltage across them.
Yeah.
Okay. So for instance, if this one was +5 on this way, and this is -5 on this side, we would imagine this to be +5, -5, +5, -5. Okay. So that means the voltage here, being measured at the center, will be the same as the voltage being measured at the center here. Because this also went +5, -5, +5, -5, because these also have the same capacitance, so they have the same voltage on each one.
Yeah. Okay,
So,
I think
yeah.
that makes sense.
Yeah. If this was like 2C, now this one matters. So now you can't do that trick. The second any of these capacitors change, such that it's not all completely uniform, you can't do it anymore.
So if that one was 2C, it would have a different voltage. So then so then there would be a potential difference between the top and the bottom ones.
Correct.
So then the middle capacitor would have an effect.
Yes. And we haven't gone over how to calculate that, so you don't have to worry about that.
Okay.
I don't know how you would calculate it. I'm sure there's like some mesh analysis or something you could do, but...
So basically in this case, you just pretend the middle capacitor's just not there.
Correct. And so then you're just solving two series capacitors and then those in parallel with each other.
Okay. Okay, yeah. I think that makes sense. Yeah.
Okay, cool. All right, nice. What's up? What's up, Ansh?
Oh, if it was 2C, wouldn't the potential difference still be 0 since they are in parallel, so they do have, like, the two branches?
But then, so the branches would have the same voltage, but I feel like the voltage across each capacitor would change. right? So so wouldn't the voltage in the center? I don't know. I feel like it wouldn't be the same as the voltage here, right? Maybe not. Let me think. So if that was 2C, and then these are in series, so then that total capacitance, the total capacitance on this leg, right, would be 1 over C plus 1 over 2C. So that would be equal to, what is that? 3 over 2C. That would be equal to 2/3 C. Yeah. Okay. That would be the total capacitance across here. And then each one of those would have the same amount of charge for the 5 volts. So I would say that Q is equal to 2/3 C times 5. So now Q is equal to 10/3 C. So now if we look at the voltage across each one, right? The voltage across this one would be 50 over 3. Sorry, no. Sorry, the voltage across this one... Wait, one second. Q equals VC. Oh, wait. And then, yeah. Q equals 10/3 C for that one. Oh, wait, no. No, they have the same charge. Same charge. Then V is equal to C over Q. Okay. So then the voltage on that one would equal to 2C over 10 over 3C. So what, that would equal to 6 over 10? No, I have this backwards. Sorry. Yeah. Q equals... That's what I wanted. Sorry. So, 10/3 C over 2C. So that would get me 5/3 volts. And then the other one would be V is equal to 10/3 C over regular C. So that would just be equal to 10/3 volts. Okay. So then this one would have 10/3 volts across it, and this one would have 5/3 volts across it. So I think the voltage in the center here would not be the same as the voltage here.
Oh, even though they are in because I know for like parallel like capacitors, they're supposed to have the same voltage, right? The same as the source.
The entire line does. So this total capacitor has the same voltage as the total capacitor here. But then when I break up that total capacitor into series capacitors, then the voltage distributes.
Okay, I get it.
Yeah. I feel like this one would like pull more of it. Is that what we said? Right? The 10/3. No, that one would actually have less of a potential difference. Yeah. I'd have to see. Because it's kind of weird because it's like connected in the center, right? So like what's the potential in the center here? Like is it 0? Because you got -5 here, you got +5 here. I guess it depends where you connect it, yeah?
Yeah. That makes sense.
Yeah.
So
okay.
So the voltages on the two capacitors on top,
Yeah.
they have to add up to the overall difference, potential difference, right?
Correct. Yeah. So this would end up being like 2.5 volts, and this would end up being 2.5 volts.
So the wire.
Oh, so so I think you're right. Good job, Em. Em, you're right. You're making lots of sense here. So I need 2.5 volts potential difference. So this would have to be 2.5 volts. Okay, there we go. I think. And this needs to be higher. Yeah. Right, in order for the voltages to add up. Let me see a diagram of that, actually. I'm curious. One sec. Potential on plates to capacitors in series. Dun, dun, dun. This is kind of a weird diagram. Yeah, we never really like. I've never seen us actually label like what the potential is on the plates. We just say what the difference is across them. But now I'm curious. Does no one do this? Let's ask ChatGPT. Chat, teach me. Let's see. If I have two capacitors in series, across a total 10 volt potential difference, what is the potential on each plate? Assume the left is 5 volts and the right is minus 5 volts. I'm just curious. Yeah, because plus 5 and minus 5 would be a difference of 10 volts on each. Okay, so it's plus 5, 0, 0, minus 5. Okay, okay. Okay, so I had this wrong. There we go. Right, okay, so the total difference, right, from here to here, plus 5 to minus 5 is 10 volts, yeah? But then the potential difference across this is 5. This is 5 volts. So then the total is 10 volts. Does that make sense, Emily?
Wait, yeah, so that would be the same regardless of
Yeah.
the capacitance.
Well, let's say like, okay, what if the rightmost capacitor was twice C? Now I'm curious. I want to see if it gets my 10/3 and 5/3. Yeah, okay, there we go. 2-to-1 ratio. So 10, what did I have, sorry? I had 10/3 and, wait, for the 2C one I had... I had 5/3, and the other one had 10/3. What do they have? They have 10/3. Then they call this one 20/3. Wait, why is the other one 20/3? One sec. Oh, you know why? Oh, I screwed this up. Sorry. The total voltage is 10. Okay, so this becomes 20/3. Yeah. And then the other one just becomes 10/3. Yeah, okay. There we go.
Wait, so if the potential on the two inner plates are still the same, then how come the...
Well, no, now the potential on the top plate is negative 1.67 volts.
Oh. And then on the bottom two capacitors, it would still be 0.
Still be
right?
0. Exactly. Yeah. Right, okay.
Oh, I see. Okay.
This is actually kind of cool. Yeah. So this tells me that the drop across the first capacitor needs to be 10/3, which 10/3 is what? 3.33, right? And this is going to be 6.66. Notice how, right, this still adds up to 20 volts of potential drop. So then going from plus 5 and dropping 3.33 means that this would be 1.67, or wait one sec. Why minus 1.67? Wait, do I have that wrong? Yeah, 5 minus 20/3. Starting the leftmost plate. 5 minus why is it 20/3? thought that one was the... Oh, I have this backwards. Oh, man. Sorry. These numbers. Okay. This one is 10. This one is 20. Yeah. This is the 2C. This is the 1C. Okay. So, yes. That's why this would go from 5 dropping down 6.67 to become negative 1.67. And then this makes sense. It's consistent. Negative 1.67 is then dropping by 3.33 to negative 5. And so, yes. Okay, so my gut intuition of internal plates here was backwards. These potentials, these voltages are the same. But in this case, it's a negative 1.67. And here it's technically a 0. That's what it should have been. Okay, cool. See, even I learn things every day. There's so much to physics.
Yeah. Okay, that makes a lot more sense.
Right? It makes a lot more sense to me too. I think a lot of times in physics, some of these things come around and like professors just hand wave and they're just like, yeah, whatever it is what it is.
Yeah.
And I'm like,
so technically,
no,
technically, if the bottom right capacitor was also 2C,
yes,
then the middle capacitor still wouldn't matter.
correct. We'd be all Gucci.
Okay. Okay, that makes
Actually,
sense.
I think if any of these capacitors were 2C, right? If this one was 2C, wouldn't you still get the same thing?
Oh yeah. Wait.
Would you? Wait. If this one was 2C, then that one would drop by... No, it wouldn't, right? That one would drop by 3.33, so that would be 1.67, and then this would be 1.67, and then this would be the negative 6.66. That's kind of cool.
So the 2C they have to be on the same side.
Correct. It has to be exactly symmetric.
That's pretty cool.
Right? That's pretty rad. I think it's dope. It's cool. Okay, yeah, thanks for pressing me on that one.
Well, thank you for explaining and going over time.
No, it's okay. It's all good. Okay, cool. Nice. All right. Yeah, we'll do another one of these tomorrow. I think same time. So I'll make an announcement during lecture tomorrow, at least. But if you want to just put it on your calendar, it'll probably be the same time. I also have I was telling people earlier, there's the whole actual office hours website. So I do this like outside of the class as well. But there's a if you go to this website, actualofficehours.com, there's a schedule here, and then this schedule has all of the times that I stream, because this is like linked to my Google Calendar. So anytime anything last minute changes, it'll be here. And then there are also some other streamers on here that do, if you ever need help with like math, some of the people here do they have like PhDs in math, so they do streams on like crazy math classes, but also like chill math classes. But yeah,
Pretty cool that like all this is like available for free.
yeah, and it's been available for free for like 5 years. It's just it's people slowly find out about it, I guess.
Also, could you post the screenshot of like what we
Yes.
just
Yes.
discussed?
I can totally do that. Also, all of these streams are recorded. Did you know that?
Oh wait, yeah, I was trying to find the office hours streams on YouTube, but
I'll help you find them.
like the last one I could find was like from May, so
Oh,
yeah,
that's in the official playlist. Yeah, I need to update that. I'll show you where they're at. Okay, let me post this one for you real quick. This was. Oh, I think this was the same one, but here I'll just update the screenshot. Was it this one? Which one was it? No, it wasn't this one. Oh, actually, I didn't post this one. Oh, I should have. Okay. Homework 8 question. Was it? I think it was 11. Yeah. No.
13.
13. Thank you. Wait, didn't I save it? Oh, I called it Emily. That's fine. Alright, there it is. And this is homework 8. Yeah, so if you ever want to figure out where the recordings are, so the main channel page, and then if you go to live here, this tag right here, this will have all the most recent streams. So this was yesterday's, this is 2 days ago, 6 days ago, 7 days ago. And then what I do is eventually I'll put them into like a playlist. And yeah, the playlist is like office hours recordings, which there's 764 so far. So.
Oh, all right. I see.
But yeah, if you click on the live tab, that'll have all the office hours. The recordings for the lectures I keep private, just so like UCLA doesn't yell at me for like giving away free education. And so those links are in Campus Bar.
Yeah.
Yeah.
Okay, that makes sense. I mean,
Yeah.
I guess technically, like, someone could just go to your office hours and ask you to like lecture on
They
like
could. Yeah.
some topic, and it would be like the same thing.
It would be. But yeah, if it was some random person asking me to like asking me to lecture them, I'd eventually like cut them off after like 5 or 10 minutes. I'd be like, yeah, but I have to help other people. Sorry. Like, oopsies.
Disqualified.
Yeah.
Okay. All right. Thank you.
You're welcome.
Bye.
Bye.
I had a couple like quick questions.
What's up,
So,
Anj?
like, the exam will it be open note as like exam 1?
Yeah, it's open whatever basically. You know, I just
Okay, so we can like.
you can go through lectures, you can go through previous questions, you can go through whatever notes you have. I just ask, I know I can't prevent it, but like ask that you don't like just copy paste from AI, just for your own sake, because you don't really learn from that. It's actually a huge issue. I went to this physics teacher conference yesterday, and it is a massive fucking issue right now in education. All the teachers are like freaking out. They're like, I don't know how to give tests anymore. Because like everyone can just get 100s on everything, and I'm like, oh no. Oh no. Okay, yeah.
Okay, that's cool. So we can use like office hours lecture recordings. and all.
Yes, totally. Yeah, you can go through any of the recordings, anything we've done. Totally cool. It's valid.
Okay, and also for the exam, like up to which homework do you recommend like doing?
Ooh, okay. Up to which homework? So you don't need to do anything with circuits. I would say up to the second to last homework, but even within the second to last homework, I think only resistivity is covered. So like only the stuff we did Monday during lecture.
Okay, so basically including homework 9?
Let's see. What's homework 9? Yes. Technically including homework 9. Yeah. I would say for homework 9, the only thing you need to really cover is like resistivity and like maybe some current density stuff.
Okay. And also, will stability be on the exam?
No, I don't think there's any stability on it. Like unstable or
Okay,
stable
got it.
equilibriums?
Yeah.
Yeah, no.
Okay, thank you.
Cool.
Thank you for the time, the office hours and all.
Oh, for sure, Asha. You're very welcome, dude. Come by anytime.
Thank you. Bye. Have a good day.
You too. Let's see, what is Fembox saying? In-person exams with no computer or phone access? Yeah, see, even that's an issue, Fembox, because I was talking to some of the professors that do in-person, and they say this is now a serious concern because students can just like keep their phone like in their laps, and especially in like lecture halls of 200, 300 people, it's impossible to police everyone. So then it's like, oh, maybe we'll require them to put their phone up on their desk and they have to put it face down. And then it's like, oh, well then some people will just get a burner phone to just put on their desk while they use their real phone to still cheat. So does you say not have a testing center? Not for 200 kids. It doesn't. It's just the lecture hall is what it is. And so before AI got really, really good, yeah, it would be pretty hard to cheat on an exam, because if you're pulling out like a phone to try to do calculations or like try to do things. And then there's also like the bathroom break issue. Like if a student says I need to go to the bathroom, you're like, you can say like, hey, okay, give me your phone, let me hold on to it. But what's to prevent them from just bringing their friend's phone in? Yeah. It just becomes this thing where teachers are now becoming basically like TSA. Like, what? Like, they have to become this, like, Gestapo, like, you know, I don't know, whatever, just trying to make sure that, I don't know, it's just kind of weird. Teachers are just supposed to teach. But I get it. The temptation of being able to cheat gets, like, pretty great, especially when so much is on the line. And especially when, like, students are having to do so much to try to stand out to go to med school. So they overwork themselves. They take on too many classes. And so they just try to find ways to survive. And survive for them is like, I have to get an A in every class. So it's weird. Wo ist haben Sie Paperin? Sensation. Do you want to be my my in-class Gestapo going around? It's the dusk of education as the sun slowly sets. Yeah, we just have to rethink it, man. I think we have to rethink the value of education and like what drives things. I think this whole GPA and grades thing just needs to go away because it just brings out the worst in things. Like, I get it, we need a metric for, like, you know, success and like accountability, but the problem is that, like, when it's just strictly a grade and there's only like so many effective ways to measure that across scale, right? 200, 300, 400 people. You're always going to have people trying to find ways to skirt the system. And as it gets easier to skirt the system, more people will do it. Like, it used to be like, okay, cool, a couple people will cheat, whatever, you know, because it used to be pretty difficult to cheat on exams. You'd have to, like, I remember my friends would do some unique things. They'd, like, take a water bottle and, like, change the inner label into, like, I don't know, like an equation sheet or something. Like, you could do some really crazy shit if you really wanted to cheat. I get it. But nowadays, yeah, from the professors and lecturers and high school teachers I was talking to yesterday, they're just like, yeah, it's a fucking war zone because you can just hide a phone just down in your lap and just quickly just, you know, picture, done, put it down, and then just AI will do the whole thing for you. So, yeah, I think ideally we'd get back to things like, you know, oral exams or, you know, demonstrating that you actually know a concept with like a project or something. But also that puts a lot of burden on the teachers. The only burden the teachers should be having is like, I need to teach. I need to figure out how to teach the concepts effectively. All this other shit of like grading and like administration and like making sure people don't cheat and like tech support, all this stuff shouldn't have been a teacher's job. Teachers are already burdened enough with like trying to find ways to like communicate like knowledge through like efficient education, that I understand why the burnout is so much. I understand why teachers just quit in droves. They're just like, I'm not getting paid for this. Like, since when did I have to also become like the hall monitor? Since when did I also have to become these kids' parents because they're not getting disciplined at home? Like, they don't have any sense of like ethics or morals because mom and dad are having to work like 4 jobs just to like stay afloat. I don't know. There's so many issues. It's very easy to get very pessimistic and bleak about the whole situation really quickly. But I don't know. I'm gonna keep teaching, I guess. That's what I do. I just teach. Anyways, okay, cool. Enough ranting for me. Let's close that stream. All right, thank you everyone for coming to Actual Education Office Hours. Appreciate all the knowledge. I know I had no time, sorry, for user questions today. We're getting towards the end of the quarter. They have an exam on Friday, and then they'll have a final exam. So I expect that my UCLA students will start really occupying a lot of these streams. It's okay. I know it's the summer. Not many people actually have homework that they have to get help with. But I hope you're learning along the way. I'm learning along the way. Like this whole question with capacitors and stuff. This was super cool. I didn't know about this. I didn't know that's how it distributes. I thought it was like +5, -5, +5, -5 or whatever. Jonathan Haight. Okay. Cool. Send me a link of that. Send me a link, Zach, of whatever article. I'll go read it. I need to get back on LinkedIn and read the things that you reshare and you repost. They're really fun. But yeah, it is also kind of funny, right? You know, at like the beginning of the quarter, like none of the students showed up to office hours. Now we have like 4 or 5 that are showing up. This always happens, dude. It's like a snowball towards the end. They all start showing up. They're like, oh man. The anxious generation. Okay, cool. Yeah, they are anxious. I get it. I'm anxious, dude, at this point. I'm very anxious, dude. I don't know what's going on. Alright, I will have another stream tomorrow at 5 o'clock. If you want to come by, probably learn some physics with us. We'll be there. But until then, let's go raid someone. Let's go say hi. Casey's working on our IRL rig. That's cool. Let's go say hi to Ask a Scientist Gaming. This guy's really cool. I love this person. They do interviews with like professors. Applied machine learning. Oh, go ask this guy some machine learning questions. Zach, AI, your favorite. All right. Enjoy the rest of your Wednesday. See you tomorrow on Thursday. Peace.